Okay, so we are now in, oh, I gotta do attendance. Oh my God, I didn't even do attendance. Well, I'm gonna pause sharing. I'm not gonna start recording again, so welcome back. We are not recording. I'm gonna go to here, and we had a question on homework 20, you said? Yes, 20?
Yes.
And which question was it?
8, 9, and 10.
8, 9, and 10. Okay, so let's look at 8. Oh my God, lots of words. Okay, our bodies have a natural electric field that is known to help wounds heal. Wow, wonderful. Does changing the field strength slow healing? A series of experiments with newts investigated this question. In one experiment, the two hind limbs of 12 newts were assigned at random to either experimental or control groups. This is a matched pair design. Matched pair, so we look at differences. The electric field in the experimental limbs was reduced to 0 by applying a voltage. So we don't got to go into the details if you don't have some physics background. The control limbs were left alone. The table gives the rates at which new cells closed a razor cut in each limb. Wow, that's that hurts. In micrometers per hour. Okay, so to access this data set. So first, why is this a matched pair design? So we're looking at the two hind limbs of 12 newts, and the two hind limbs, one was the control, one was the experimental. So these are matched because each pair is the same newt. So it's a matched pair design because the control and experimental limbs are matched by the newts, because the newt's ability to heal in one leg is not independent of the ability to heal in the other leg. We can't just look at 12 newts left leg and 12 newts right leg, because newts are all different. If I really want to see the difference, it has to be the same newt, so I can compare the two different voltages, one when it's applied and one when it's not applied. So it has to be, so it's a matched pair. We have to match them up. Now choose the correct stem plot for the differences between the limbs. So let's take a look. 36 minus 28, that's 8. Here's 8 right here, 0 to 8, 0, 8. 41 minus 31 is 10. That's right here, 10, right? We've done 7 leaf plots, right? Is this what your question was, the 7 leaf plot?
No, I guess it was just it was like trying to figure out what like the first part was and how that made sense. And then if you scroll down, there's also other clarification questions. I think I was just struggling on how to like pinpoint which one it was. That was my struggle.
Okay, well, first, Angel said question A is C. It's a matched pair design because each newt has two hind limbs that can be compared. That's true, but I think A is a little more in detail. That's what's shown in the solution. I mean, I'm not saying C is wrong. I just feels like A is a little more explanatory. I mean, the first option is a little more explanatory. I mean, they can be compared, it's true, but we can go further. Yeah, I would never ask a question like that. It's so vague. Okay, so if mu is the mean difference in healing rates, what are the null and alternative hypotheses? Well, the null is always the equal sign. There's never a question about that. So the second one's immediately out. And then we want to see whether or not one is better than the other, right? The control limb minus experimental limb. We want to see if when we apply the voltage, they heal faster. If they heal faster, so what are we measuring here? The rates at which cells closed. So we want the rates to be higher in the, gee, this question sucks. The control limbs were left alone. So does it slow healing? There we go. Does it slow healing? The experimental limb, if we apply the voltage, does it slow healing? Does this one go down? So because it's control minus experimental, if this one goes down, control minus experimental should be a positive number. So the alternative is that it's greater than 0. Okay, so it took me a couple minutes to get it, but there it is. Mu is greater than 0. And then carry out a t-test. Well, okay, I can do that. I can go to crunch it. And then I can do statistics, and I go to T, and this is a paired sample, a matched pair. First variable would be the EXP, the experiment. Oh, hello, dinner. Thank you. No, I'm good. Thank you. Experimental. Second variable is the control. Right? That's the order that we had it in, correct? It was control minus experimental. Control minus the experimental. And we want control minus experimental to be greater than. The mean difference is 0. Experimental minus control. We might just switch those. Let's take a look. Yeah, so we had it backwards. So let's do it again. This should be the control. This should be the experimental, and calculate. Okay. Oh, so it was A. Okay, good. Okay. So null hypothesis that it's 0, alternative that's greater than 0. Average difference was 6.4, 11 degrees of freedom, one less than the number of things. T statistic was 2.076, p-value 0.0316. What's the conclusion? P-value of 0.03. What's the conclusion?
Reject the null hypothesis.
The p-value is between 0.025 and 0.05, right? We got 0.03. I'm sorry. So I had asked you, but I was a little distracted. I'm sorry. Did I answer your question yet, or have I not gotten that far yet? I'm sorry. The one who asked this question, I apologize. Did I answer it yet?
Yeah, I was just trying. I was gonna ask how you did the crunching thing, but you just did it right now, so now I know how to do.
Okay, good.
Thank you.
Now there is an outlier here. There is an outlier, right? If you actually look at the data, this data here has this guy all the way out here, 31, which is an outlier. So the question then says, carry out a t-test that omits the outlier. So if we go back here and we just say, okay, let's ignore this one and let's erase this data. I don't know if I can erase the whole line or not. Edit, it's selected maybe, no, okay. Let's see what happens if I do it now. T paired. Oh, look at that. I get a smaller T statistic and a greater p-value. But you'll notice that the p-value is still greater. Sorry, the p-value is still less than 0.05. Is it? 0.04477? I wonder. No. Oh, whoops. This wasn't necessarily the outlier. The outlier was the 31 came from, not from 3023, which was good data.
Difference.
Hold on, I'll start this again. The one that we're going to delete is this one, the 8th. This, the 31 came 5625. So it's this one that we're getting rid of. So now when I do it, there we go. So now we get a t-value of 1.79. and a p-value is more than 0.05. That's right. Someone asked if the p-value is less than the cutoff point, it's always reject the null hypothesis. That is correct. So notice that when we admit the outlier, we come to a different conclusion because now it's not less than 0.05, assuming that was the cutoff point. So does the outlier have a strong influence in your conclusion? Yes, it does. At the 5% significance level, the null hypothesis is rejected when the data includes the outlier, but not rejected when it does not include the outlier. Does that make sense? I hope so. Oh, that hurt. I'm not having a good day, guys. I am not having a good day. Okay. Okay. Next one also, you said? Number 9? Yes, no, maybe so?
Yes.
Okay. Researchers claim that women speak significantly more words per day than men. One estimate is that a woman uses about 20,000 words per day, while a man uses about 7,000. To investigate such claims, one study used a special device to record the conversations of male and female university students over a 4-day period. From these recordings, the daily word count of the 20 men in the study was determined. The table contains their daily word counts. Use the software of your choice to make a histogram of the data. Okay. Well, I like Crunch It. Does it give me any details for? Okay. Well, let's take a look. How many bins should we have? It goes from 4,000, a little under, to up to 40,000. So let's do 5 bins. Let's see what happens. Okay, so that's a pretty nice histogram. What value should we remove from the data to make it reasonable to use the T procedures? Because remember, in order to use T, we have it come from a normal and from an SRS, right? But there can't be any outliers. Are any of those data there an outlier? What do you think?
It's also dependent on the sample size, right?
Yeah. The larger the sample size, the more you can get away with. But outliers are always the issue. So this outlier here, 37,000, is so much larger that, I mean, especially, maybe I'll come back here and I'll use more than 5. Let's take a look. Let's do, let's say I use 10 bins. Harder to see, but still this is skewed to the right. So if anything's going to be an outlier, it's going to be this one way out here. So with this data removed, assuming that now a t-test is appropriate, carry out the test. So let's go ahead and do it. First, let's remove it, which is that one. And then let's carry out the t-test. One sample t-test. And what are we testing? Is it different than 7,000? We're testing if it's different than 7,000. So what should the mean be in the null hypothesis?
7,000.
And the alternative?
Not 7,000.
Right? Not 7,000. We'll use the words as my sample. We'll calculate. So what do we get as my p-value?
.44%.
0.4%. Very small. So here already is the known alternative. X bar is 1.156 times 10 to the fourth. That's 11560 approximately. What's S? They don't give me S, but I can calculate it because remember the standard error had a formula. Standard error was equal to S over the square root of n. So if I have the standard error and I multiply it by the square root of 19, I can get S. So when you do that, you get S. What's T? Well, 2.258. They give me that. What's P? They give me P. So P is very, very, very small. There's overwhelming evidence that the mean number of words per day of men at this university is not 7,000. Now, the sample mean, which is 11,500, indicates that we know it's different, but is it different less than or greater than? It certainly indicates that it's different greater than. Does that make sense?
Yes.
Okay, good times. And we're 24 minutes in, so if you want to say after class, I can do the last one, but I got to get started. Is that okay?
No, yeah, 10 is like 9, so I think it's fine. Thank you.
Were there any decision for exam 2? Oh, I'm meeting with him tomorrow. Not tomorrow. It was going to be Friday. It's going to be this Friday. So we have no answer yet. Holding pattern. I talked to him, but we haven't had a group meeting about it. So holding pattern. Okay. So next, I'm going to stop sharing for a minute because people asked me to use slides again. And I was like, I'm sorry, I don't have any slides. But apparently I might have slides. So let's load up Canvas. I'm going to close that. I'm going to close that. I'm going to close that. I'm going to close. Oh, no, here's Canvas. So courses. And I'm going to go to Math 140 Common Resource Site. Now, what chapter are we on? Have we done 21 yet?
We finished 22 or I think we finished 22, or you stopped midway because you said you didn't want to get too far ahead.
Oh, wow. That's amazing. Let's look at his PDF for chapter 22. And I'm going to download this. Or I don't have to download it, but I will start sharing my screen. And let's see how this works. So you can thank Ali Al-Sharaka, who is my boss. I really should know how to pronounce my boss's name, but I don't. Anyway, inference on a population proportion. Okay. So I'm not sure why he's doing this again, but we know what statistics is, and the whole point of statistics is to draw inferences and make conclusions. We have hypothesis testing. we have confidence intervals, our two major methods of inference. Here are some symbols that we're going to be using a lot of. Capital N, which we haven't really used because it hasn't really mattered, is the size of the population itself. What we've used a lot of is lowercase n, which is the size of the sample. Lowercase p was the proportion of successes in the population, which we do not know. If we knew it, we wouldn't need a sample. So instead, we take a sample and we calculate p hat. P hat is the sample proportion. Now, you can do lots of samples proportions because you can take lots and lots of samples. What's the average of all the samples? That's going to be mu p hat. This is the average of the p hats. This is the standard deviation of the p hats. This is, of course, the actual average of the entire population, which I don't know. This is my sample mean that comes from my sample. And if I take lots of samples, I'll get lots of sample means. And this is their average, mu x bar, the average of the sample means. The standard deviation of the sample means, the actual standard deviation, and my sample standard deviation. So we've used most of these before. Some of them we haven't really come across yet, but we've used most of them. We did this. Stop me if I ever think we did something what we really didn't, but I'm pretty sure we did this. P hat is the proportion of successes over trials. Okay. Right. This is all stuff that we did, correct? I'm trying to match up where we were with these slides, so I need your input here. Right? Is this something we've done?
I don't think we've done that yet.
What in my notes I have?
I mean, we did all the hypothesis tests, right? I can't find anything. I think we did, but just in case, let's go through it. What the hell? Nothing wrong with repeating. So, the sample distribution of a proportion p hat is the number of successes over the number of trials. So you have a population. You take a sample of size n. You get a sample proportion. Another sample proportion. Another sample proportion. You do lots and lots of them. Every sample of size n gives you a sample proportion. If I would then go ahead and look at the distribution of all of those sample proportions, what I would see is lots of them cluster around a specific value, which is the actual value for the original population. And as I go further to the right or to the left, I kind of deviate significantly from that. That's where we stopped. Okay. So the standard deviation of this distribution, the distribution of sample proportions, is given by this formula right here. The square root of p, 1 minus p over n. Of course, I don't know p. That's kind of like the whole point. So what can I use as an approximation for p since I don't really know p?
P hat.
It's the best I can do. Use p hat. So even though the actual sigma for p hat is this, I can't actually use this. So what I do instead is replace it with p hat. Okay, so for the sample proportion, we take an SRS, because we always want an SRS. We take n trials from the population. The actual fraction of successes, what we don't know, what we'll never know is p. Our statistic is our sample proportion of successes. Now, as a rule of thumb, what we're going to use, and I think we mentioned this, I hope we mentioned this, is that if the number of successes and the number of failures is both greater than or equal to 15, it's considered large enough to use this approximation. The book might be a little different, but again, it'll be fairly close. Okay, and it's subjective. There's no like And God said, if it's not bigger than 15, you can't do it. It's roughly that value. So the center, as we saw here, of all my samples that I do, all those lots and lots of samples, they're all going to cluster around the actual value. So the average of my p-hats should be the actual average of my actual p, my population. The standard deviation is bigger the lower the n is, right? If I make n big, my denominator gets big, my deviation gets small, and this thing narrows in size, which is why we like big samples, because we have sharp peaks when we think we, at the location that we think they should be. Okay, so quick question. As a sample size increases, does the sampling distribution of p-hat become approximately normal? This is the whole idea. As n gets larger, hey Chitron, remind me to fix it if I forget. As the sample size gets larger, it becomes more and more normal. If it becomes more and more normal, we can use our formulas that apply to normal distributions, which is why we like big samples. So here, in 2012, about 24% of high school seniors reported binge drinking, which is defined as 5 or more drinks in a row in the past 2 weeks. A SRS of 500 high school seniors is to be taken. What is the standard deviation of p-hat, the proportion of high school seniors in the sample who would report binge drinking? What is the sample? What is the standard deviation? So, oh crap. Well, that's all the answer there. But we have the formula. It's the square root of p, 1 minus p over n. P is 24%. 0.24. 1 minus 0.24, which is 0.26, divided by 500, divided by n, square rooted, but they threw something extra in here, so this is out. Here they left out 0.76. Here they left out the square root. But here they have p, 1 minus p, all over n, and then square rooted, correct? So just by plug and chug, D is the correct answer. I went too far, I know, but so here's one that I won't go too far. So true or false? It is true. The sampling distribution of a statistic is this. It's the graph of all my samples. Lots of samples in the middle, not a lot of samples in the end. This is a sampling distribution. So the sampling distribution is the distribution of values taken by the statistic in all possible samples of the same, from different populations. I didn't even read that part. From different populations. Well, that makes it false. Okay, everything was great until the last 2 words, from different populations. It's the same population. All right, it's one population. And then we take samples from that population and we look at all the different samples and each one will have an average. Yeah, no, I get it. I made the same mistake. I thought it was true until I actually read it. And then I realized, oh, wait a second. I should read the whole thing. Okay, so here's another one. For any population proportion P, the standard deviation of the distribution of p-hat gets smaller as we take larger samples. That's the results of large samples are less variable than the results of small samples. Is that true? Ali tricked. Yes. I will let him know that. Ali tricked us. So this one is true. Right? We know it ends in the denominator. As n gets larger, it gets smaller. Okay, so confidence intervals. We spent a lot of time on confidence intervals. I'm trying to see where we're at. But just quickly, because it's never bad to review. I thought as n gets larger, p gets bigger. No, why would that be true? As n gets larger, x probably also gets larger, right? So as n gets larger, p, which is x over n, approaches its true value, but that could be larger, smaller, stays the same. It could be anything, right? Okay, so we did confidence intervals, right? You believe it's pretty close to a certain value. For example, 90% confidence interval. I get this. It's being multiplied, right? P. It's being multiplied. P. What does that mean? It's being multiplied. Sorry, I'm not understanding your question. What does it's being multiplied mean? As to why it's getting larger. Well, who said P is getting larger? Right, P is the number of successes over the number of trials, correct? So P, as n gets larger, the number of successes will probably also get larger, and that ratio is just going to approach a specific value, correct? The standard deviation, on the other hand, as n gets larger, P and 1 minus P are probably not changing that much because they're probably close to where they should be, and the denominator is getting bigger, which is why this thing should be getting smaller as a general rule as n gets larger. Does that make sense? Hopefully that makes sense. So then we did square roots and square roots, well, no. Because square roots make the denominators, yes, that's true. Sorry, you're right. No. If n gets bigger, the denominator gets smaller, correct? But if I square root n, then I'm not making the denominator as big as I would otherwise, which means the fraction is not going to be as small as it would otherwise, which means actually the square root is not helping make it smaller. It's just the math has a square root. What can you do? Right, 1 over 4 is 0.25. 1 over the square root of 4 is actually bigger. It's a half. It's 0.5. So the square root makes it bigger, not smaller. Right, Angel? You're looking up into the air like you're trying to calculate this. Yes? Okay. Well, trust me, I'm a doctor. Okay, anyways. So confidence intervals are the form, the center, plus or minus the margin of error. We've talked about this. You have the lower endpoint, the upper endpoint. The width of the interval is twice the margin of error, because the margin of error is just plus or minus. Plus or minus, you go both ways, twice as much. How do we estimate P? Well, we estimate P using P hat. It's the best thing we can do, right? We don't have P. If we had P, great. We don't have it. So we will estimate using P hat, okay? We talked about this. We did confidence intervals already. We have the requirements for when you're allowed to use this confidence interval. And we know what the form is. We spent some time on that last week. I want to focus on hypothesis testing. So we talked about this. We talked about how to find the correct sample size. We talked about that. So let's get to the hypothesis test parts. Okay, test of significance, the 4-step process. State the question. Identify the parameter that you are trying to determine, mu or p usually, okay? State the null and alternative hypotheses. We've done examples of these, and choose the type of test. The greater than test, the less than test, the not equal to test. Make sure the conditions hold, SRS, normal, that whole thing. Calculate the test statistic, find the p-value. And then use your conclusion, right? So we've done a lot of examples of these. This is not new. So let's, right? So again, what are they? You have a null hypothesis, alternative hypothesis. You calculate your test statistic. You calculate the likelihood of being past it, which is called your p-value. And then you decide whether to reject or not reject the null hypothesis, okay? We always start off assuming the null hypothesis is true. Remember, every test is assuming the null hypothesis is true. And then the question is, do we come to the conclusion that we will reject it or not? But we always work. If you look at crunch it, remember when crunch it, what's that thing that we fill in the table? It says mean under the null hypothesis, right? We're using what the null hypothesis is claiming as the basis for our math, okay? The null hypothesis is usually the status quo with no effect, and we seek to reject it. That's the goal. We want to reject the null hypothesis. Otherwise, why are we testing it? If we're happy with it, why test it? And even if you really want it to be true, but you got to test it anyways, when I say we seek to reject it, that's not always necessarily true. We don't always want to reject it. But the question is, do we conclude that we're going to reject it or not? Okay, so we start off assuming it's true. We take the sample, we look at the sample evidence, and then we decide what to do, okay? So for example, if the null hypothesis says that P is 0.75, then we should expect to get a number close to 0.75. The further away from 0.75, the more likely we are to reject the null hypothesis. Of course, we know that in reality, we don't expect to get exactly 0.75, even if it's true. So then the question is, well, how far away do I really have to be before I reject it? And this is where the test statistic and the p-value come in. So the alternative hypothesis will be the same as the null hypothesis, except the equal sign is replaced with a less than, greater than, or not equal to sign. For example, if H naught, the null hypothesis is P is 0.75, and we want to show that P is different than 0.75, then what would we write? We would write not equal to, right? If it's less than, we would write less than. If it's greater than, we want greater than. It depends on the problem. They're all different. But you've done homework already by this point. You've seen examples of these by this point. You read the question and you decide, what am I trying to test here? Okay. So here's a detailed example. We've done these before, but never a bad idea to see more. The pollster found that among the 360 voters sampled, 261 planned to vote to re-elect the governor. How apropos for today, even though it's not governor, but whatever. Can the governor safely conclude that he has over 70% support in that country? Okay, well, let's take a look. The null hypothesis is that P is exactly going to be 0.7. The null hypothesis is always the equal sign. And he is asking, do I have more than 70% support in that country? Well, then if I reject the null hypothesis, I would reject it in favor with being greater than 0.7. What's my actual observation? 0.725. Hey, that's greater than 0.7. But is it far enough greater than 0.7? Well, let's take a look. Our test statistic is 0.725. That's the cutoff point in the green in my little chart there. So what's the p-value? What's the probability of being past that? Well, so they did the math for us. They got 0.8508. That's 85.08%. Which means my p-value, which is the probability of being past it, is 14.92%. If I use 5% as my cutoff, and 5% is right here, by the way, if I were to use 5% as my cutoff, would I reject or not reject the null hypothesis in this situation?
You do not reject.
You do not reject the null hypothesis because you're greater than 5%. Notice that you're not past the cutoff point. This is the cutoff. 0.725 is not quite there. Therefore, I would not reject it. Even though it's more than 0.7, it's not enough more than 0.7 for me to reject the null hypothesis. In fact, my z-score is only 1.04. 1.04 means if it was 0.745, then I would reject the null hypothesis because that's past the 0.74, which means my p-value is going to be less than 5%. Exactly. All right. So how do we actually, sorry, but I have yeah, of course, go. I hope everything's okay. Testing for P. Okay, so what is the null hypothesis? Okay, that P has a specific value, P naught, P sub 0. And what we're going to do is we're going to calculate the test statistic. Okay, now I've given you this formula before. It's your data point, your sample value, minus the mean, divided by the standard deviation. This is just the z-score. It's the z-score in the context of a sample proportion, where the mean is the same as the underlying mean, and by your assumption, it's this value. And the standard deviation is the square root of p1 minus p over n. Of course, I don't have this value. Well, I guess I do have this value. It's what I'm believing to be true, right? I do have this value. So I can actually compute my z-score under the assumption of that value. Notice the big difference here between this and the confidence interval situation. In the confidence interval situation, I did not have a guess. I did not have a p naught. I did not have a p0. So I had to use p hat because it's the best I have. Well, I haven't taken my sample yet. I don't have a p hat. What's the best I have here? It's my guess. It's what I'm assuming to be true. So for the confidence interval, for the hypothesis test, I use p naught. Even though for the confidence interval, I use p hats. Very similar, but conceptually very different. And I can have a less than, I can have a greater than, or I can have a not equal to. All right. And what do? We reject h naught if the p-value is less than alpha, as always. What is alpha? 0.05, unless otherwise stated. So far, I think this should be okay. Right? This is all stuff that we did, right? You're okay with this? Right? I hope it's okay. So here's a question. We hear that newborn babies are more likely to be boys than girls. I think we did this one, did we? Well, just in case we didn't, let's do it again. Presumably to compensate for higher mortality among boys in early life. A random sample found 21,800 boys among 40,000 firstborn children. Is this sample evidence that boys are more common than girls in the entire population? Well, it's certainly more than 50%. The question is it enough more than 50%? So our null hypothesis is that it's status quo. They're equal. Why wouldn't they be 0.5? And we're testing whether it's greater than 0.5. There are conditions to be met. Assume they're met. Let's just assume they're met and let's move on. So A, B, or C. Is there, there's very strong evidence that more than half of firstborn are less than boys. Is P less than 0.001? Very strong evidence. There's no evidence that more than half of firstborns are boys. P is greater than 0.1. Or it cannot be calculated. Of course, these are not all the possibilities, but still write out the formula. So what is my Z statistic here? Z is, we just had it in the previous page, the actual p hat, which is 21,800 divided by 40,000, which is 0.545, minus the assumed value of P under the null hypothesis, which is what?
0.5.
0.5 over the square root of the assumed value, 1 minus the assumed value over n, which is the sample size. So 0.45 minus 0.5 divided by that times the square root of that. And I get a z-score of 18. Let's forget the p-value for a second. What does a z-score of 18 tell me? Where am I falling if my z-score is 18? Where am I at? Where am I at? On the normal curve, my z-score is 18. Where am I at? Am I in the middle? Am I in the left? Am I in the right? Anyone? What does z-score tell you? Is anyone there?
Is it the probability?
Nope, I'll stop you there. It's not. The z-score tells you how many standard deviations you fall away from the mean. If I land 0 deviations from the mean, where do I fall on my curve?
Center.
The center. If I fall 1 deviation from the mean, where do I fall on my curve?
The 68%.
I know what you're saying. Okay, it's the point where 68% would be 1 deviation left and 1 deviation right. And if I fall 2 deviations to the right, what percent will I have covered there?
95.
And if I fall 3 deviations right, what percent will I have covered there?
99.5.
And if I cover 18 deviations, where do you think I'm going to land?
99.9 times a million.
Okay, I don't know the exact number, but yes, it's way out there. The p-value is certainly extremely small. So I don't know exactly what it is. I'm sure a calculator can do it for me, but it's very, very small. All right, quick question. A manufacturer is concerned the defective rate of a manufacturing process has increased over the historical value of 3%. So he's worried. So he takes a sample of 300 parts and he checks 12 of them. Oh, sorry, he checks 300 and 12 of them are defective. What is the appropriate test statistic in this situation? Is this a P situation or a mu situation? Are we looking for an average or a proportion?
Proportion.
Proportion. So what is our formula? What is our formula? So it's P, 1 minus P over N all square rooted. That's certainly part of the formula, but it's not the whole formula. Our Z statistic, Z equals what? It's hard to
X bar.
focus because of the, it's hard to focus because of the presidential race going on right now. I always find that when I study math, the cares of the world just drop away. Don't you guys? Just study math and don't worry about it. Is that any consolation? Not even a little. Not even a little. All right. Well, what can you do? Maybe we'll end early because people aren't focusing. Well, not quite yet. Z is our actual value, which is 12 over 300. Whatever number that is a decimal. Minus the value, assuming the null hypothesis is true, which is what? 0.03%.
0.03.
Divided by the square root of our assumed value for P, 1 minus the assumed value for P over N. So Sean, I have not yet, tell me at the end of class, I'll do it then, okay? Because I don't want to. Okay, so 0.03, 1 minus 0.03 over 300. That's this one. That's not this one. That's not this one. And this one's the only one that has minus 0.03. I assume that this guy here is 0.04. Otherwise, I won't keep a pairing as a possibility. So the answer is B. Do I even hear someone listening to a news report right now as I'm teaching? I can hear it. That is hilarious. All right, well, this takes us to the end of 22. And it's the presidential stuff today. Nobody's paying attention. So okay, well we can call it here. I'll give you guys the rest of class off. You guys go and get all excited or disappointed as to whoever wins and loses, and come back next time, please, reinvigorated for a full class of math. Okay, no excuses next time. Even if your guy does not win, you got to make sure to get over it by Thursday, or at least to. I am not going to watch it myself. I really don't care. I am not. I'm not politically oriented. I'm kind of apathetic to life in general. I know people say to me, "Well, if it affected you, you'd matter." They say to me, and I go, "Listen, man." I go, "I was diagnosed with I told you this. I was diagnosed with pre-diabetes 2 years ago, and I did nothing about it. I don't care whether it affects me or not. I just don't care about anything in life. I like my math books, my physics books, my chemistry books, the things that I'm interested in, and I just let the rest of the world go by. It's great that you're passionate about these things. Well, yeah, I mean, I have my interest too. You know, I mean, chess, tennis, martial arts are things that I do 100%. What I'm saying is everyone should have the things that interest them, and that's great. And you should be very passionate about something. I think it's amazing. It's just not something that I'm very passionate about. So I don't mean to disappoint or anger anyone. If you're if this is something that you are passionate about, that's not what I'm trying to do here. I'm just being honest. I just like the things that I like and nothing else. So I will not be watching it. I mean, I'm certainly curious as to what happens, but not curious enough to like watch it religiously and see the tick marks going up. And it's like doing what you love because life is too short. That's right. YOLO, girls and boys. YOLO. See, I know some slang. Do people still say YOLO anymore? I don't even know if they do or not. But YOLO. You only live once. So I don't know. I said. I remember I was playing chess once, and I was in a tournament, and I'm looking at the board, and I'm studying it, and I'm studying it, and I'm studying it, and I'm like, what do I do here? And I'm playing a guy who's so much better than I was. Like there was no way I was going to win. But I'm looking at the board. I'm like, wow, I can make a major sacrifice here. And should I do it? Should I do it? And I look up at him, and he looks at me, and we make eye contact. And he must have known what I was thinking because he goes, YOLO, man, YOLO. So I did it, and then I lost anyways. But it was fun while it lasted. So yeah. My very first tournament, I lost to a 7-year-old. My very first game, I lost to a 7-year-old. He did something that I thought was a mistake, and I'm like, oh man, what an idiot. So I like jumped on it, and it wasn't a mistake, it was a trap, and I'm like, damn, I'm an idiot. It was horrible. So yeah, there's some good ones out there. All right, anyways, guys, I'm gonna stop recording now.